Good morning, everyone. This is Larry Welch with the Texas Asphalt Pavement Association, coming to you from our headquarters in Buda, Texas. And we're trying something new this morning. We're doing kind of a live broadcast with our beautiful faces here. And I'm with Gary Fitz again this week, or this month. Gary, glad to have you here this morning.
Thank you very much.
We're going to be talking about polymer modified asphalts and things like that. Just a couple of things. Our next webinar will be January 16th. That'll be the third Thursday of the month. And we're going to have Jim Warren joining us that day. We're going to talk about balancing production rates on asphalt pavements. We do record all the webinars, and they are on our library, on our website. If you go click on that, look at education, the first thing that pops up is webinars. You can click on that and go down, and you can view any of our webinars from the past year. Also, I want to remind you of our big asphalt conference that we're going to have February 12th and 13th, 2020. At San Marcos, Texas, at the Embassy Suites, right off of 35. You can register online right now. You can view some of the speakers that are going to be there. We have a great flyer that we're emailing a lot of people around the state, and we hope you will join us. We're shooting for about 600 people, so I'm hoping everybody that we contact and know about the MAPS conference, that's Managing Asphalt Pavements. It's kind of a catchy topic. Will be with us those 2 days. For that great conference. We got a lot of speakers lined up that you really enjoy it, learn a lot about asphalt pavements. So if you want to look at some of our things on our website, the calendar events, you can go there also. So without any further delay, I'm going to turn it over to Gary. Gary, start off and we're going to run with it, all right?
All righty. This is kind of a new experience for all of us doing the studio version or in-studio version. Last time I was working out of a hotel room up in Richardson. So this will work. We'll see how this works. I think it's going to work out very well from what we've seen so far.
Could you just tell them to maximize their?
Oh, yes.
Yeah, go ahead.
You can maximize your screen. You can drag it and pull it up full size on your computer. Also, if you'll mute your computers, that'll keep anything from coming back to us. Also, there's a chat box. If you have any questions, just type those in. I'll be monitoring those. That chat box, and I can break in with Gary at any time and we can try to answer your question. I think that's got us all covered, and we appreciate everybody that's with us this morning. Thank you very much. So Gary, we'll go right on into it.
All righty. Okay, this is really part two. We had the first introduction back about a month ago for this, and what we're going to be covering this time is we'll go back and review or summarize what we went over in part one. We'll be talking also about the next generation of asphalt binders, which we feel is a game changer, and what we refer to this as is highly modified asphalt. So we'll be taking it to the next level as compared to what we've done in the past with polymer modified binders. And then we'll summarize the storage and handling guidelines for polymer modified asphalt binders that the Association of Modified Asphalt Producers has produced. First and foremost, just to introduce the company I work for, Kraton Corporation. I showed this slide last time as well. Again, this was the company that actually invented SBS polymers back as part of Shell Chemical in the 1950s. And we continue to be a major manufacturer of that and want to think of ourselves as being on the cutting edge of developing new asphalt binders, not talking about polymer modified binders, but talking about the basis first and foremost. Then we moved into polymers and PMA binders, and then talk some about the performance. And we'll cover each of these things just in a very brief way before we get into highly modified asphalts here this morning. The definition of an asphalt binder from ASTM, as you can see here on the top. I don't need to read that for you. We know what color it is. There's a lot of terms that are used for this. Bitumen asphalt binders are the most common ones. I'm going to try to stick with asphalt binders as I go through here, but forgive me if I use one of these other terms as we go through. Most of the use of asphalt binders as produced by the petroleum refining industry are as a binder for aggregates for producing hot mix or as a sealant or waterproofing material that can be used in a variety of applications, including in roofing applications. We see some used for coatings for undercarriages of vehicles that are prone to damage from salt spray and that sort of thing, and other types of things, even in the makeup business, cosmetics. You see some asphalt used for that. Not a very high percentage, obviously, but it's got a variety of uses, as it has had ever since its development initially. This is a little example, and I pulled this, it's not directly from the Shell Bitumen Handbook, but the information comes from there, so I cite them here at the bottom. And this is just showing you what happens in a simple refinery, which is the basis for producing asphalt binders in a refinery. Crude oils are selected based upon a variety of things by the refiners, but in this case, what we're going to assume is that we do have a crude slate that is amenable for producing asphalt binders. Not all of them are, but in this case, what we're seeing is the crude will come into a furnace where it's heated, goes into atmospheric distillation, which is just a giant still. And so you have a series of trays in there at which different materials at different boiling points are captured based upon their condensation temperature. And then that material that comes out of there or that's left behind that doesn't boil away is referred to as long residue, goes back into a furnace where it's reheated, and then goes into vacuum distillation. And what happens here is the reason for vacuum distillation is in order to simulate the effect of going to higher temperatures without the prospect of cracking or breaking down the molecules that make up asphalt. And so what you're doing here is mimicking that process. And what comes out of this is you get some additional types of fuel products that you see listed there. And then the short residue or vacuum tower bottoms that comes out of that can be processed to make a heavy fuel oil, or it can be used as a coker feed or used for asphalt binders. According to the Energy Information Administration, about 1.5% of the products or the output of asphalt refineries in the United States were asphalt binders in the past year or so. And you can look up that information. That varies a little bit as the year goes on because the types of runs they're doing at the refineries vary throughout the year depending upon the demand. But that's about the average that you see for a yearly basis now. Now, going directly into specifications for asphalt binders used in hot mix, the performance graded specs came into play back in the mid-1990s as a result of the Strategic Highway Research Program's asphalt research studies, which actually work was being led in Austin, Texas by the University of Texas and Professor Tom Kennedy back in the day. TxDOT in the late 1990s, as many other states did, adopted the performance grade specification. And where this is different than previous specifications is instead of having varying the temperature that you're measuring or varying the criteria that you're measuring for, or like you do for other petroleum products, let's say setting a standard temperature and then changing the criteria, you establish a criteria and then you change the temperatures at which you test it so that you're able to meet those requirements over a range of temperatures that relates to what you're using them for in the actual pavement. And so with this, when you see these numbers, those are actually temperatures in degrees Celsius, and they represent a range of temperatures that under normal conditions that you would expect an asphalt binder to perform suitably to resist rutting and cracking. Another specification has been developed since then, because remember, this is 20 years old and there's been all kinds of developments, as we know, in our everyday lives in equipment and computer and that sort of thing. And so what's happened is we found some better parameters to use using the same types of tests, but to give us better, I guess, properties that we can use within the asphalt binder to assure that we get better performance out of materials. And those are characterized in AASHTO M332, which is being used to replace M320. And I have a slide coming up that shows where that's happening right now and the evolutionary process that's taking place to bring that into play around the country. This is just an illustration of those PG binder tests, and these are the same whether you're using the M332 or M320 specification. And you can see that we're testing at a range of temperatures and at a range of aging conditions to represent how the asphalt binder is when it's placed and compacted, and then how it is after some time or how it changes over time that can be related back again to the performance of the asphalt binder in a hot mix asphalt mixture. This is just a screenshot of item 300, table 17, that's out of the 2014 TxDOT standard specifications. And so I'm not going to go through this into gory detail here, but you see a series of grades up here at the top. The high temperatures represent what we refer to as the high temperature grade. The low temperatures that you see listed down below that are low temperature grades. And you can see where I've labeled over here on the left-hand side the properties or the tests that are being done that relate to handling, rutting, fatigue, and low temperature cracking. We'll come back to this later on to show you where you have an extra requirement that was placed in the TXAPA specification that refers to polymer modification, but we'll talk about that when we get to it. Some additional requirements that are as part of a special provision that's been enacted by TXAPA is that the suppliers have to meet the asphalt binder quality program that's described in TEX 545-C. And so again, you can go in and look up any TXAPA test procedure, specification, et cetera, on their website. One important reason for pointing this out is just so that people understand that the suppliers have to go through a rigorous means of testing and quality and establishment of quality control plans and that sort of thing in order to be qualified suppliers for TXAPA projects. And that's something that has been, I guess you could say that the requirements on that have increased over the years. And I think that's a good thing both for the suppliers and for the contractors and for the industry in general here in Texas, is to set good standards and then to stay with them. Other things that you can see here that are highlighted down towards the bottom are some limitations in some additional materials. If we want to get into that with questions, Larry, we can do so, but what these do is limit the use of an additive that's called polyphosphoric acid to no more than 0.5% by weight of the asphalt binder, and the use of what's called REOB, or re-refined engine oil bottoms, to no more than 5% by weight of the asphalt binder. These additives are both used and have been used successfully for many years as means to blend in with asphalt binders to modify or to have some slight modification to their characteristics. What this does is it controls their use to it so that the use of these materials isn't excessive and cannot have a deleterious effect. I mentioned the AASHTO M332 specification, and you can look this up on the Asphalt Institute's website because I just pulled this off as a screenshot as well. And you can see where a number of states have adopted M332 and or portions of that for their modified grades that they're using. And currently, TxDOT is evaluating the use of the main difference in AASHTO M332, which is a different type of thing that comes off of the dynamic sheariometer, which is called a multiple stress creep recovery, or MSCR. Some call it massacre test. At any rate, there's a recovery test that's part of that, which is very simple and easy to do, and it's very repeatable compared to other types of recovery tests. And that's something that TxDOT is looking at as a potential for implementing to be able to apply this to modified binders or grades that require modification in the future. I mentioned modification, and now where that leads us directly into polymer modified binders. When you see grades that have greater than a 90-degree useful temperature interval or difference between grades, and these numbers, that's 70 minus 22, it's not 70-22 that you see up here on the screen. So anything that's greater than that doesn't always require that from a supplier or refining standpoint, but generally speaking, most of the time when you see a grade greater than that, a supplier is going to need to modify that, often with the polymer, in order to achieve those. Now, additional requirements such as an MSCR recovery or elastic recovery requirement will basically force that, because the asphalt itself can't comply with that specification without having that sort of a modifier within it. The most common type of modifier that's used for that is SBS, or styrene, butadiene styrene type polymers, which have the effect of increasing the high temperature grade without changing the low temperature grade much. So what you could say it does is it stretches that useful temperature interval out by expanding the high temperature side and increasing that difference. Also, if you have a elastic recovery or MSCR recovery requirement, you can't meet that usually without using an elastomer such as SBS. And in the TxDOT specification, this is in the current version, elasticity comes in there with the elastic recovery test. As I mentioned before, what we are seeing right now is they're evaluating the ability to use the MSCR recovery test as a replacement to that, because it's just a simpler, much more convenient, and much more repeatable test to be used. Now, when we talk about SBS, what exactly are we talking about? These are styrene block copolymers, is what we call them, as one of the manufacturers of those materials. And this is where you have, what you're doing is you've got monomers, which are the building blocks for this. The way that they're linked together gives you qualities in that material that can then be imparted into the asphalt by incorporation, and that's where the modification comes in. With this, what you see is the polystyrene is a very hard type of substance. The polybutadiene is what's connecting those things together, and that's a very soft, rubbery thing. And so when you put those things together, you're able to get both types of characteristics, something that is resistant to deformation as well as something that snaps back once it's deformed. And there's where the modification comes from in terms of the physical effect that you have on the asphalt binders from modifying with an SBS type polymer. This is just an illustration of what asphalt binders act like when they are not modified. And so you'll see this video is going to play for about 30 seconds. And so I'll be quiet for a second and let you watch this. As you can see, the binder specimen stretches out, but it doesn't come back or recover its characteristics. Now let's take and do the same thing with an SBS modified asphalt binder. And so we're pouring mold just like we did before. The same technician takes it out. First thing you notice, it's a lot more difficult to pull this thing, so it's a stronger, tougher material. And then as the technician sits it down, we see that it's able to recover its original shape, which is the definition of elasticity. And so when I talk about elasticity, and whether it's measured with an elastic recovery test or using the MSCR recovery or some other type of test that characterizes elasticity, that's the characteristic, that it comes back or it doesn't remain permanently deformed. It comes back to its original dimension that way. Now, polymer modified asphalt performance has been looked at for some time. Since these things have been in place, or we've seen different versions of specifications since the 1980s when they were originally introduced. A study was done by the Asphalt Institute, or for the Asphalt Institute by Applied Research Associates. Harold von Quintus, who is one of their chief engineers who lives up in Round Rock, was the fellow that actually led the study on this. One thing about ARA is they were also involved and have continued to be involved with the implementation of the Mechanistic Empirical Pavement Design Guide, which is the new version of the Pavement Design Guide. And what that did is that did some field studies, and then they were able to develop transfer functions that looked at material qualities of materials in pavements and relate those to damages done or observed out there in the field. And so they're able to relate field performance to laboratory performance in that way. In this study, what they did is they developed or identified pairs of test sections where there had been tests done over the years that looked at where you had control sections that had unmodified binders, you had test sections that had modified binders. And so from those paired sites, they're able to do a similar sort of approach as they did for the MEPDG and develop those transfer functions, and then allow that to be compared allowed a comparison to take place between the polymer modified asphalt binder performance and the unmodified asphalt performance in the same mixtures. These studies are reported in these publications that you see listed on the screen, and they're available through the Asphalt Institute website. Now, looking at this and just kind of pulling a bunch of the results of that all into one thing, they developed a damage index that you see down here on the bottom there. And looking at modified asphalt versus convention, you can see looks like at least the color on my screen is maroon. The plot on the right there is the characterization of that for polymer modified asphalt mixtures. The one in blue is for conventional mixtures. And what you see there is the improvement in performance when you're taking all those factors into place, looking at that damage index. And what you see is about a 50% improvement on the pavement life that results from using polymer modified asphalt versus conventional on those pavements that were observed in the field. Now, what's going on with polymer modified asphalt binders, and typically is what you look here at the top on that part of it with about 2.5% polymer, and that's you might not see that used on any particular modified binder, but that's in the ballpark of what you would see used for some of the modified binders that we see here in Texas. And what you get from that is the polymer goes in there, and then it's going to absorb some of the oils within the asphalt, and it will expand or swell. But what you wind up with there is an asphalt binder which has been changed by the polymer characteristics in there, but the phase of it is still being controlled by the asphalt binder or by the bitumen. And so what you have is polymer that's kind of suspended within there but the asphalt binder is really the still primary factor that influences the response to load and the performance of that binder. If you look down here on the very bottom, what you see is kind of the opposite condition, to where there's enough polymer that's in there to where indeed what you have is a network of polymer that's formed within that binder, and the asphalt is simply serving really as the carrier for it. So you could almost call that an asphalt extended polymer as opposed to a polymer modified asphalt. And when we talk about highly modified asphalts, that's where we're going with this. What you see in terms of the effect of that on the response of the asphalt is when you develop that continuous phase, you wind up having a case to where you have drastically increased some of the characteristics as compared that are controlled by the polymer in this case instead of by the asphalt. You can see where you get up in this particular example above around 6% polymer loading on this is that the characteristic or changing characteristic flattens out. And so where you've got a consistent response on that. And in this case, you're looking at the softening point or ring and ball type of test, but you would see the same sort of reaction if you're looking at things such as G star over sine delta or any sort of measure of resistance to deformation at a high temperature. You can see the same thing if you look at recovery as well. Well, when you get up to that phase is what we refer to as highly modified asphalt or HIMA. And so you'll hear me use that term as we go on through. And it is what it says it is. It's more than double the amount of SVS that's being used to create something like a 76-22. The important thing is you're developing that continuous polymer network. So the polymer is what's controlling the performance of the binder, not the asphalt. And what this allows you to do is to have a much tougher binder, which is going to simultaneously provide resistance to cracking and to rutting. And we'll verify that on some of the slides that are coming up here. A lot of work has been done at the National Center for Asphalt Technology test track over at Auburn, outside of Auburn University. This is located about 100 miles southwest of the Atlanta airport there in eastern Alabama. And the way this is operated is you've got continuous truck traffic operating 16 hours a day, 5 days a week out there on the track at a speed of around 45 miles an hour. There's a 3-year cycle in terms of the construction and testing and monitoring that takes place out there. And so there's been a series of test sections that's been put out there. I believe that started in 2000, didn't it, Jim? Somewhere around that time, but this has been going on for almost 20 years now. Well, Kraton developed some test sections back in 2009 to evaluate the performance of highly modified asphalt. And what they found in the laboratory was a much higher fatigue endurance limit for the Kraton base mixture than what you saw for the conventional asphalt mixture. And the rutting resistance was much greater, improved as well. This was validated when they looked at the performance of this after this was under traffic. This went through a couple of cycles of traffic, which amounted to around 20 million equivalent single axle loads, and was essentially non-distressed by the time it was completed on that. And this was a very thin section of pavement also. And so this was something that impressed the researchers there and impressed some of the other sponsors at the NCAT test track. And I'll be showing some photographs of some images from a nearby test section that was constructed by the Oklahoma Department of Transportation not too long after that, where they applied the highly modified asphalt to rehabilitate it. And that opened some eyes in terms of success of it. And that led to another project that I'll also be describing as we go through. Since that time, several other test sections and other uses of the highly modified asphalt without any of Kraton's input really have taken place. One of them that's currently underway right now is they have a cracking experiment, which is in the second loading cycle as we speak now, about halfway through it. In that, what they're trying to do in that is they're looking at a number of the tests that are used on hot mix to try to characterize resistance to cracking, such as the ideal CT, the Texas overlay test, the IFIT test from Illinois, and so on. And they're looking to see which is the best performance predictor. They're looking specifically at top-down cracking. So they've got a half dozen test sections there. And what they did is they designed these test sections so that they can try and induce top-down cracking. So what they wanted was a pavement section that would deflect, that would move under load, but would not crack from the bottom up. And so what the researchers and sponsors decided to use on that was a base mixture, which was 4.5 inches thick, that placed in 2 lifts that used the highly modified asphalt so that this would bend, but it wouldn't break, would help induce cracking to take place at the top so that you could get that comparison between the cracking test results on the surface mixes and the actual cracking that took place in the field. That all is ongoing, but one thing that has not happened is that there hasn't been any cracking in that base that's been reported or observed, and so their design of this worked. To me, that's a very impressive result because, again, you got a very thin pavement. This is moving under traffic, it's bending, but it's not breaking, and it's not rutting either. So that's what they were trying to see, and that's what we've observed. They've also did a mix with 35% wrap, looking at high modulus asphalt mixtures, which have been used for many years in France as a means of being able to reduce the thickness of the pavement structure and essentially have something that you could say is black concrete out there, but doesn't, where you don't have to cut the joints into it. This is going back over the original site at NCAT. Again, they used a 5 3/4 inch total thickness for this. And what you see there was excellent performance was observed on this, where there was essentially no distress. Everything backed up what was seen in the laboratory on this. That performance after 2 cycles is what led them to look at the Oklahoma, or looking at this as an opportunity to rehabilitate a section for Oklahoma, which was causing problems out there on the site. What happened with ODOT is they had built in the 2006 section some test sections to evaluate the perpetual pavement concept for a project coming up on State Highway 152 southwest of Oklahoma City. This was new construction that was going to take place, and what they did is they hauled some of the famous red dirt from central Oklahoma over to Alabama. They rebuilt the embankment to give put actual Oklahoma materials in there in support that would be indicative of what they expected out there on this project there near Oklahoma City. They put in a 14-inch section, which they felt would be a perpetual pavement section, but in order to test this or to compare it, they also put a 10-inch thick section in there, which was meant to fail, so they could be able to see and contrast the difference between those things. Well, indeed, the 10-inch section did fail, and it was so severely distressed that they had to rehabilitate it for safety purposes for the operations of the trucks on the test track there. After they rehabilitated it, and what they did was they milled out 5 inches and came back and replaced that with some polymer modified binders in the mix and with SMA on the surface, and they had geotextile there between the surface course and the underlying course. That failed after about 4 million ESAL. And so this was, again, leading to problems on the test track and had them scratching their heads about how are we going to fix this to where we're not having to go out there and do this over and over again and having it cost us a lot of money. And so having observed the performance on a nearby test section using the highly modified asphalt, they decided to go ahead and try that. So what they did is they milled about 6 inches out and they replaced that with mixtures which all contain the highly modified asphalt binder. And what happened on this, and this is a very busy graph up here on the upper left-hand side, you can find this in some of the NCAT reports. And if you need that, you can contact me and I can send that graphic to you directly. But basically what you can see from this is that the roughness and the rutting stabilized after that rehabilitation. And there was no cracking observed until after 15 million. That is almost a cycle and a half of traffic after this fix was placed on it. And what they did not do on this is they didn't go in beneath that 6-inch layer. So they didn't try to fix anything or do anything to stabilize or reclaim what was underneath this. This went back on materials that were cracked and they were moving around. And this impressed Oklahoma DOT enough to where they had a project out on Interstate 40 in 2012, and they applied the same concept there. Now, back in the day, I used to have to travel across from Oklahoma City to Amarillo on occasions. And when you get out there west of Oklahoma City, you would have thermal cracking. So it would seem almost like you're driving over a jointed reinforced concrete pavement with regular cracks about every 50 or 60 feet. Boom, 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 boom. That, and you also had other type of distress due to traffic and so on that had taken place out there. And so they thought this was a good example of an opportunity to go and maybe use this approach to fix this. And so that's what they did. They let the contract to where it was built between February and April of 2012, as you see here. And again, this is about 50 miles west of Oklahoma City between milepost 102 and 104 out there in Caddo County, Oklahoma. I went up there, I had a meeting in Oklahoma City on the 1st of August, and so I took the opportunity to go out there and pay a visit to the project. And this doesn't look very exciting in terms of traffic or anything, but it took me a while to have to wait out the trucks to be able to get out there and take these photographs. So it's not what you see here. I should have videoed that instead of showing still shots, but I did it anyway. At any rate, as I went through the project, and I went through both directions on this several times, I observed no cracking and no rutting, and this is after 7 years of interstate traffic. The amount of traffic out there, by the way, was about the same truck traffic volume as you see on US 75 or North Central Expressway around McKinney, Texas, north of Dallas. So it's a pretty significant amount of traffic. Again, this is where it is. On the Oklahoma DOT website, you can go in and find pavement management data that's very specific to sections of interstate on there. It's very convenient for people like me to go in and look at. And so I went in and dug that out. And what we found on that was the roughness data that was taken and recorded earlier this year showed an IRI of 53 in one direction, 50 in the other. Those would gain, for a brand new pavement, ride quality bonuses for schedules 1 and 2 for new construction here in Texas. And I would challenge people to go out and find the newest concrete pavement that was built to see if those had IRIs at this level. Not saying anything bad about the competing material, but go find some of those. Well, changing the focus back to something that we might see a little bit more often, and that would be on resurfacing and applications in that respect. The New Jersey Department of Transportation kind of went the route that TxDOT's going in developing mixtures very similar to the TOM mixes that we see used, especially in the Austin district, but are spreading around the state years ago. They call it a high performance thin overlay or HEPTO mixture, and they do have balanced mix design requirements that go along with that. And what happened, that they had been using that for a while. The New York City Department of Transportation decided to take advantage of that. So they borrowed that specification and they utilized that for resurfacing of a 17-inch thick jointed reinforced concrete pavement that had been built in the early 1980s on First Avenue in Manhattan. Now, this roadway is a major arterial street there in Midtown Manhattan, and this gets all kinds of interesting traffic. You have all the delivery trucks and everything. This time of the year, you get snow plows and all this sort of thing. Probably the worst thing that attacks pavements in that area is Con Ed, which is the utility company, going in and cutting out and patching and doing those types of things. So we're not immune from that too, but they suffer from that badly up there.
And then you have taxis and the trash trucks that come through all the time.
Oh yeah. I don't know if the taxis cause that too much problem, but the trash trucks, and again, signalized intersections every place you go along there. At any rate, to make a long story short, the pavement was in bad condition, was very rough, and was causing all kinds of problems with it. Now, the city of New York also has some of their own hot mix plants, and they'll do their own work out there very often. I'm not advocating that by any means, but what they typically see out there is about a 2-year replacement cycle on their hot mix surfacing. So they expect there in Manhattan to put something down and then, due to all kinds of reasons like I described, come back and mill it and replace it within a couple of years. Well, using the HEPTO mix, as I describe it here, with the highly modified asphalt, they did about 53 blocks on there at night in 2013, and it's still there. The picture you see on the right was one that I took back in April as I went out there and walked along there. Now, they didn't allow the utility companies out there for 5 years, and they have been out there since then. So there is some patchwork that's taken place through there. Some of the cracks or the joints from the concrete pavement have reflected through, but they've all held intact. There's very little spalling out there. And again, this surface is considered by them. If you look at the New York City DOT website and you look at the pavement condition on there for First Avenue, it's considered in good condition throughout the stretch of that project. Now, I mentioned the HEPTO mix uses a balanced mix design approach. Kraton a few years ago had PaveTex do some work for them looking at a TxDOT mix, taking a TxDOT Type C mix and applying the balanced mix design approach to that as well. And this is before it became really popular, but what we wanted to see was what can you do with this in order to look at being able to prevent rutting and control cracking simultaneously. And what you see with this is that when you get up to binder, when you're able to get binder contents high enough with this, you're able to gain drastically improved resistance to cracking without severing resistance to rutting at the same time. Now, in the past, we've had something we called grade dumping in Texas. I think this maybe give you an opportunity to do something that I will call grade jumping as we look forward to this, if we're allowed to do this as part of a balanced mix design. I think this is another variable that could be considered as you're looking to meet some stringent criteria as we look ahead to where specifications are going in the future on this. Let me stop right now. Larry, are there any questions or anything coming up?
Nothing has showed up. Again, if you'd like to put some questions in the chat box, I'll be reviewing those and can insert those in, and Gary can answer those. But feel free to type into that chat box. But right now, I don't have anything.
Okay. Moving ahead, the Florida Department of Transportation adopted what they refer to as high polymer as part of their standard specifications in July of 2017. And where that came from is they had observed the work at NCAT as well over the years. They're active participants in the NCAT test track, and so they participate in all that. They saw what was going on there too. They had a project on, there was a section of US Highway 90, which was just west of Tallahassee in Midway, Florida, which was a persistent problem for them over the years, that you have 2 truck stops along there. And what was happening was you had a lane in which the trucks were slowing down, coming to a signalized intersection, and then turning into a truck stop. And that there was persistent rutting that was taking place over the years. The DOT was looking at going in and pulling that out and replacing with Portland cement concrete, but as a stopgap measure decided to give this a try. So they milled out and replaced 2.5 inches with mixtures. This would be their dense graded friction course mixture using high polymer binder in 2014. This was meant to be a trial, to be something just to patch them over for a little while before they could go out there and put concrete pavement in. Well, these pictures were taken back in October of this year. And so what you can see there is on the left-hand side, it's not a close-up of it, but you can see several trucks lined up and then turning. And that's where a lot of the problem was, although it wasn't exclusive to that, but that's where a lot of the issue was, and that's what was causing the problem. Going back and taking a photograph right there at that stop bar, as you can see, there's no rutting of any consequence that's taken place over there. And going through the project itself, walking up and down through it, there's no cracking either. I got this information from the state bituminous engineer from the Florida DOT out there when I was visiting the site. And if you look at the blue line there, what you can see is that's the rutting that Florida DOT recorded with their automated device in 2014 before they milled and resurfaced the project. And you can see rut depths that are up to 2 inches in places, and doing manual measurements, I was told up to 2.5 inches in places. Down on the bottom, you see in the red what was most recently measured on those same pavements using the same technique earlier this year. And as you can see, there's very little rutting. This was kind of the eye opener for FDOT and help push them to make the decision to include this as part of their standard specification to replace the PG 82-22 that they had previously used in there, with the intent of using this primarily in areas where there was a history of rutting. And this is just some more detail about that. Now, what this also led to was some research project that FDOT did in recent years. And so what they did is they contracted with the Texas A&M Transportation Institute for a research project to evaluate the differences in open graded mixes or something similar to our PFCs using the high polymer binder versus PG 76-22. And what the results of that, this was published back in May of this year. And you can find this on the FDOT website. And again, if anyone wants that, I can be happy to provide them a link or or I can send the document itself. But the conclusion on this was that they expect more than a 50% increase in service life. And that is with respect to how much time it would take to replace as a result of raveling or predicted raveling taking place in that surface as compared with the PG 76-22. Using cost data that was provided by the Florida DOT, the researchers at TTI also concluded that this was a cost-effective application for this. Now, FDOT also had a project with the University of Nevada, Reno, looking at how you characterize this material for pavement structural considerations, looking at dense graded mixes. They can continue for asphalt pavements to use the AASHTO 1993 pavement design guide. And in that case, you're using layer coefficients to characterize the structural contribution of each layer in the pavement structure. The conclusion on that was that the contribution of layers with this was around 20% greater than it was for conventional materials. And where FDOT plans to implement this really is to kind of buy them as a factor of safety. They're not looking at trying to reduce the thickness of their asphalt pavement layers typically for this, because they use generally thin pavements anyway, and it wouldn't be realistic or practical to do that. But in areas where you see truck traffic increase, like we've seen in Texas on our interstates, and especially in the energy areas, such as in the Permian Basin and also in South Texas, that using something like this in those cases is a means of buying insurance that you didn't have before and allow you to get the pavement structure that you need to be able to accommodate the types of loads and traffic that we see these days. Now, what I've done is provided as an example a draft special provision for TxDOT to consider for item 300. And so you can see that on the right. And what that does is just provide it's just in the TxDOT format and provides a similar look to that. What this does require is an MSCR requirement that incorporates features from the M332 spec that I mentioned before. It also uses a -28 grade, which is another means of being able to get both the cracking resistance and the rutting resistance that we're hoping to achieve from this. Now, what type of applications does this make the most sense at? You're not going to want to do this anywhere and everywhere, because yes, there is a price tag that comes with that. But you look at areas where there's a real demand coming from traffic in terms of heavy traffic or the need for extended performance, places like PFC mixes on the interstate. You don't want to have to, if you can do something that's going to allow you to increase the cycle even slightly of having to mill and replace that, would be a very cost-effective application for this. And in fact, there is a special specification that's been approved for a single project use here in the Austin district for a high-performance permeable friction course that includes the high polymer specification within that I showed you before. Another application would be for thin overlay mixtures. Again, where you have heavy demands and heavy traffic, places where you do not want to have to get back out there and have to deal with it, where you're going to expect extended performance. Microsurfacing and slurry seal are something that we've seen also, where people that have applied those have noticed improved performance from that as well. Structural applications is something that I believe are important as well. Things such as I was talking about, especially in the energy corridors, where you have very heavy, both in terms of volume and in weight traffic, being able to go in there, put something down there that is of a reasonable thickness and gain the improvements in performance with respect to fatigue resistance and rutting resistance at the same time would be perfect examples of applications for this. And in urban areas, bus pads, intersections, things of that nature would be important also. Again, down at the bottom, I didn't put grade jumping. That's my term. I need to trademark it, I guess. But that's what I'm talking about as far as being able to maybe use this as a variable in terms of being able to optimize mixture designs.
Hey, Gary, we did have one question typed in.
Mm-hmm.
They want to know how thin the layer tested at Auburn was. I guess that's the NCAT test track.
Okay, at NCAT, there have been highly modified asphalt mixtures have been put down in various thicknesses. Mm-hmm. The initial test section was you had 3 layers that totaled to 5 3/4 inches. Right. In subsequent things, such as in the cracking experiment that I described before, there's 2 layers that add up to 4.5 inches in that base mix in the cracking experiment. In the base, in the high modulus base mix, I forget the thickness on that, but it was in the same order of that. And it's been used on some surfaces that were down to 1.5 inches thick. What they did on the rehabilitation, they milled out 6 inches there on that Oklahoma DOT test section, and then they replaced that with 6 inches to bring it back to profile.
I see. Okay, good. Hope that answers the question you were looking for.
Okay. I'm going to move on and talk about things that apply to high polymer, but also apply to other polymer modified binders as well. And that is just some information that the Association of Modified Asphalt Producers has developed with respect to storage and handling modified asphalt binders. One thing you want to be careful about for this, and I think specifiers, engineers need to be aware of this as well as they're looking at their overall system and specifying projects, is to avoid having to juggle around too many materials. And this is especially true when you start getting into areas where contractors are setting up asphalt plants for specific projects, where there's limited tankage and that sort of thing. What you want to avoid is having multiple grades and having the possibility of unavoidable contamination or dilution of grades by having a polymer modified asphalt mixed in with an unmodified asphalt. So let's say if you've got half a tank full of PG 64 minus 22, and then you've got a project, you've got some mix that requires 7622 coming on top of that. Well, if you blend those materials, and assuming they're coming from the same supplier, you may have just diluted yourself right out of specification by combining those things. And so you want to make sure and avoid that. And I think that's an obvious thing, but it's just kind of like when you're looking at mixes, you want to try to avoid having just tiny dabs of, and having mix designs that apply to maybe 1 or 2 truckloads. Try to have consistency, design the project to be built, and then to execute it to be built by avoiding these types of things during production and construction. This is just kind of adding on to that. And if a dedicated tank isn't available, try to get it down as low as is practical, but then come back and try to top the thing off as far as bring several loads back in so that you're able to get something that is likely to comply with the specification before you crank up and go forward with that. Vertical tanks are something that that's been found to be very amenable for use when you're looking at using polymer modified asphalts. Most SBS modified asphalts aren't going to have any issue or concern with respect to separation, but if one is using ground tar rubber modified asphalt, that can be an issue with that. So that's something that you'd want to coordinate that with suppliers about. But what vertical tanks allow you to do is to have more efficient agitation and be able to circulate material around better to keep it suspended so that you avoid having issues like that take place during construction. Horizontal tanks are common and have been used. The main thing there that you want to make sure is that you have circulation to be able to achieve uniform temperatures and to move material around and avoid having excessive or extended contact with heating coils. You want the suction and return lines to be at the opposite ends of the tank to completely turn it over, and the return line near the bottom, again, to have material being completely flipped around within the tank so that you're not keeping it held stationary or steady like that. Again, we talked about mixing asphalts or having materials coming from having modified materials blended in with unmodified and therefore diluting it out of spec. One thing you want to be very careful about, and this does happen in the real world, there's issues sometimes, I know from my background, is that sometimes a contract would have to switch suppliers during a project for whatever reason. It's always best to go in and just let's go ahead and test some of this in the laboratory and see what we can get away with here as far as are we going to cause any problems when we do the switch over on this if we have any amount of polymer modified binder from supplier A remaining in the tank when supplier B comes in, because it's almost certain that those are going to be starting with different base binders that they're going to modify. They probably have different technologies that they're using for modification, and those things don't necessarily, they're not necessarily compatible with each other. So it's best to go ahead and check those things out beforehand rather than to wait until after the fact and start going back to your suppliers and say, what did you give me here? When indeed they gave you something that met spec, but when they came together with something else, that pushed them out of spec or caused some practical problems to occur in the field. We
have one more typed in question. What modulus value can be used for a modified base layer in FPS 221?
That's a beautiful question. I've been trying to play around with FPS 21 as a matter of fact, and I've had some problems doing that. The NCAT reports will go through and have a lot of detail with respect to modulus values over a range of temperature conditions that can be applied to highly modified asphalt. If you ask me to shoot from the hip on that, I would say probably at an average temperature, you're looking at something that would be in the 700, 750 PSI range. But again, one problem with it is that the modulus varies with temperature. It's not as variable as it is it's not as variable with highly modified asphalt as it is with routinely modified asphalts or unmodified asphalts. It's less temperature susceptible, but there is some variation there. And so, like when I've run mechanistic designs using ProRoad with this, what I've done is going into the NCAT data, I've picked out modulus values that are representative of different temperatures, which represent different seasons, and then apply those within ProRoad to that.
I got you.
That's not a direct answer to that. That's something I probably need to talk to the questioner directly about, because the right answer is it depends.
Well, Frank, you sent that question in. You could get Gary's number there on the front of our webinar, and you could give him a call if you need additional information on that.
Okay, we got.
Thank you for the question.
All right, handling at the plant again. What you want to avoid, as well as I touched on before, is any areas where you would have extended contact with direct fire heaters with any of the material in there, because a hotspot like that can actually break down the polymer. And so ultimately, if you have something like that happen for a period of time, you can wind up moving the material out of specification if you're not careful. So again, these practices are just general best practice things that you can find. Again, this is published by the Association of Modified Asphalt Producers, and you can see their logo on the bottom right. They have an annual meeting every year, and unfortunately, next year it conflicts with the MAPS meeting.
That's true.
So at any rate, you can find a lot of good information on their website as well. Probably the most important thing of things, and I know this question comes up sometimes, is about temperatures for storing and mixing, and this is not for doing mix design work. This is for handling in the field. This comes from the Asphalt Institute as well as from AMAP, but you see the numbers posted here for PG 76-22. These numbers would also apply to the highly modified asphalts. With the types of SBS systems that are being used for that, that allows you to handle that polymer loaded binder at the same sorts of temperatures as you can typically with 76-22. And information about the pumps, about making sure that you have adequate size on this. The asphalt binder, the modified asphalt binders are going to be stiffer than neat asphalt binders. And so you need to have an adequate system in terms of pumping in order to be able to move the material consistently that way. You need to have strainers there with larger holes, and that's something that needs to be routinely cleaned out too.
Very much so.
A lot of this stuff is pretty much common sense, but it's important to review it anyway about circulation. Again, keep the material in motion is the best way to do that. And looking at the hot mix plant itself, again, you're going to have something which is going to resist movement a little bit more. And so that's going to increase the amperage or the draw and amperage that you have on the conveyors at the plant. And so, trying to get everything warmed up before you move forward is an important thing. But starting at a reduced tonnage rate to kind of allow yourself to kind of almost ease into it, I guess, is a good way to approach that. And again, your suppliers are always willing and able to talk with you about these things as far as handling modified binders, and take advantage of that. And that will be the last slide, and I think I'm on time.
All right, we're doing great on time. Are there any questions somebody would like to type in before we sum this up and sign out for 2019? We're going to be in 2020 pretty quick.
Let me do this. I'm going to go ahead and move this all the way back to the top because it's got my phone number and email address there.
We do have another question. What are your thoughts on completely removing the use of reobs and PPA? I think some of the producers are moving into reducing the reobs because of some of the small issues we've had with that. But
well, one other thing that's happened is you saw the special provision to the specification, I believe, also extends to seal coat binders as well, as far as the limitation on use of re-refined engine oil bottoms.
right.
My preference always is to, specify what you want and then allow the industry to be able to provide that. And some of the other things that are being looked at, not just in Texas, but around the country, are other parameters that are somewhat developed to help try to in some ways, if those things can have bad or deleterious characteristics or add those, then looking at those parameters can help control any excessive use of it. And probably the most common one that's been applied is what's called delta TC, which is the difference in the critical temperature for low temperature grading. So there's two ways, there's two tests that are used for low temperature grading. One is there's one test, it's a bending beam rheometer, but there's two characteristics, the stiffness and then the M value. So the difference in the temperature, the critical temperature M value versus that for stiffness is what's called the delta TC. What's been found is that if materials, and Reob's not the only one, but if some materials are used which increase that delta TC beyond a certain point, that pavements tend to be more prone to premature cracking. And so we've seen agencies go in there and try to prescribe limits to control that. And then on the PPA issue, PPA is sometimes used in helping make polymer modified asphalt binders. So it's not an unusual thing at all. Generally speaking with that, when they get, if you say you can't use it, then you're going to be handcuffing your supplier in some cases. If it's used excessively, then often you'll see that wind up coming into play in the Hamburg or into moisture sensitivity tests, where you'll see or you can see interaction between that material and some of the materials used as liquid anti-strips or hydrated lime if it's used as an anti-strip within the hot mix. My preference is to let the tests tell you what you need, and if they don't, to find out a way to do that. We've seen those materials used for many years, and I hate to throw the baby out with the bathwater. I completely agree with not trying to avoid the excessive use of things like that,
Sure.
but the test and the criteria ideally should control that.
All right. I think we've had a great webinar. Gary, I want to thank you very much for being with us for the past 2 months and going through these. Again, we've recorded these and they will be on our website under webinars, under the library portion. You can review these again. We actually had our faces shown on this one for the first time. It's kind of neat.
Live from the studios of the Texas Asphalt Pavement Association.
We really appreciate everybody. We had 71 call-ins, which is quite a number. And again, we don't know how many people are behind those call-in areas. There could be a number of persons. So we want to increase every month. So tell your friends. We send out a blast email to remind everybody of these. Again, one more time, I want to remind you about our asphalt conference in February, the 12th and the 13th at the Embassy Suites, just south of San Marcos, right there on I-35. You can go to our website and register for those right now. That registration is open, and I'll be going around here after the first year to everybody that I can get to in San Antonio up to Austin, promoting this activity. So again, we want to thank you very much. This is Larry Welch, and we'll be signing out. We want to say just have a great holiday. Everybody be safe, and we will catch you in January 2020. Thank you very much.
Thank you very much, everyone.